Hey there. Welcome to a story that will shatter what you thought you knew about World War II aviation. On a cold November day in 1943, over a French airfield, an American fighter, an icon of industrial might, crashed into enemy hands, revealing secrets that would forever change the course of aerial combat. How did a rugged, heavy aircraft like the P-47 Thunderbolt, dubbed Beetle, challenge the very notions of agility and strength? Could a single captured plane expose the staggering technological gap between the United States and Germany? And what do these revelations tell us about the true power behind victory in the skies? Imagine a pilot facing fuel running out, engine sputtering, yet still steering toward what he perceives as safety, only to be surrounded, disarmed, and examined by enemies who previously thought it unwieldy and slow. How did the Germans' initial dismissive assessment of the Thunderbolt's sluggish low-altitude handling give way to awe as they uncovered its astonishing high-altitude speed, unmatched durability, and advanced engineering? What secrets did the Germans find in its turbo supercharger, its armor, and its complex cockpit? Features that embodied American innovation and industrial resourcefulness? And how did the relentless disassembly and testing of these aircraft reveal a truth more profound than any single weapon? That the real battlefield was shaped by the staggering scale of American manufacturing capacity? So, the question remains: could the Germans, with all their technical expertise and meticulous analysis, ever bridge the vast gap of raw industrial power that the Allies wielded? The answer is clear. This story is not just about a plane, but about a war won not only by pilots and tactics but by the unstoppable force of an entire industrial system. And right now, the most astonishing insights into that system are about to unfold. The journey into the heart of American engineering mastery begins here. On the 7th of November in the year 1943, a tense and perilous scene unfolded over the skies of France, specifically at the Carpic airfield situated in the region of KH. The atmosphere was thick with the tension of an intense headwind that battered the aircraft and relentlessly drained their fuel reserves as they crossed the treacherous expanse of the English Channel. Second Lieutenant William E. Roach, a skilled pilot assigned to the 358th Fighter Squadron within the larger 355th Fighter Group, found himself in a desperate, increasingly perilous situation. His gauges indicated that his fuel was rapidly approaching empty, the ice-cold reality sinking in that his aircraft's Pratt & Whitney R2800 engine was beginning to falter, sputtering weakly as if warning of impending failure. Roach was now faced with a seemingly impossible decision. Helplessly watching the dwindling fuel supply, he knew that just ahead of him lay the safety of England, closely within reach, yet undeniably distant due to the critical shortage. Beneath him stretched a sprawling mosaic of fields in France, some familiar and friendly, others under the control of German forces, their patterns visible from his cockpit. One particular airfield caught his eye. It was eerily similar in layout to the Allied base he could recognize, sparking a flicker of hope amidst the chaos. Carefully, he committed to his final approach, aiming to land on a strip that might still hold some promise of safety. The enormous Republic P-47D Thunderbolt, whose serial number was 42-22490 and which had earned the affectionate nickname Beetle, touched down on the grassy field with remarkable grace and stability. Following a nearby ground vehicle to a designated parking area, Roach shut down his engine, only then noticing the Balkan Crow insignia painted on nearby aircraft. To his profound surprise, the very enemy he had been engaging with just minutes earlier now encircled his aircraft at gunpoint. Rifles aimed in a show of force and interrogation. The Germans, having just fought fiercely against him and his squadron, now surrounded him with an intensity that underscored the unpredictable nature of war. Lieutenant Roach's combat service for this particular engagement had come to an end. He would spend the remainder of the conflict confined at the notorious Stalag Luft III prison camp, yet his capture marked the beginning of a deeper and more significant chapter, one that would challenge and reshape German perceptions of American military technology and industrial prowess. When the Germans examined the wreckage and components of Beetle in the days that followed, they would uncover insights that would change their understanding of modern warfare material, revealing a level of manufacturing sophistication previously unknown to them. The P-47 Thunderbolt was not merely a fighter aircraft, it was a symbol, an embodiment of American engineering ingenuity, prolific production lines, and extensive material resources. Over the subsequent year and a half, as German engineers and scientists meticulously disassembled, examined, tested, and even attempted to fly captured Thunderbolts, they faced a stark and unsettling truth. It became evident that Germany was not merely lagging behind in technological developments, they had been operating in a radically different realm of industrial warfare altogether. The story of captured P-47s, which eventually fell into German hands, underscores how overwhelming a substantial material edge can be when wielded effectively in combat aviation. Proper deployment of industrial superiority could make tactics, pilot experience, and even the most skilled flying inconsequential in the grand scheme of the air war. The Thunderbolt's technological and manufacturing excellence served as an unmatched lesson, a challenge and an eye-opener for German engineers and military strategists, one that they desperately needed but could never fully implement within the constraints of their own resources. Germany lacked not just the raw materials but also the massive industrial infrastructure required to produce such aircraft at scale. They did not have the luxury of time, nor the advanced manufacturing capability to incorporate the American innovations into their own wartime machinery efficiently. The capture of Lieutenant Roach's P-47 on that fateful day in November of 1943 was not an isolated incident. German forces had encountered the formidable Thunderbolt in combat many times before. Since April of the same year, when the 4th German Fighter Group first escorted American B-17 bombers deep into enemy-controlled skies over occupied Europe, German pilots had been aware of the Thunderbolt's presence. Yet initial German combat reports conveyed a mix of disdain and confusion. Traditionally, their pilots favored more agile fighters like the Focke-Wulf FW-190 and the Messerschmitt Bf-109. Aircraft renowned for their nimbleness and agility at low altitudes. Nevertheless, the American P-47 struck German pilots as an anomaly, an excessively large and seemingly cumbersome craft, sluggish when operating at lower levels, and seemingly designed without full consideration of the nuances of aerial combat. The German assessment of the Thunderbolt was marked by skepticism, even ridicule, yet it also concealed an understanding that this aircraft, though unwieldy in appearance, the Luftwaffe personnel understood the significance of what they had just captured. Throughout the spring and summer of the year 1943, combat reports from German fighter units consistently highlighted the P-47 Thunderbolt's notable shortcomings, particularly its meager rate of climb and cumbersome handling at lower altitudes. Moreover, they regarded American pilots as somewhat hesitant, seemingly reluctant to engage in the traditional turning dogfights that the Germans valued highly. The prevailing assessment among experienced Luftwaffe pilots was that the Thunderbolt was inferiorly designed, with a tendency to be outmaneuvered during aerial combat, especially at medium altitudes where most engagements occurred. This initial judgment, however, would soon be recognized as dangerously incomplete. Despite the superficial weaknesses, Certain details in other combat reports pointed to more alarming qualities that starkly contradicted the narrative of American inferiority. Pilots reported that once a Thunderbolt opted to disengage and enter a dive, it became nearly impossible to catch, thanks to the aircraft's remarkable speed and maneuverability when descending rapidly. They also noticed that P-47s wielded 8 heavy machine guns, each firing with devastating destructive power, making their attacks exceedingly lethal once mounted. Additionally, these reports mentioned that the armor plating on the Thunderbolt appeared remarkably resilient, almost impervious to the standard 7.92 mm rounds typical of German fighters, and often capable of resisting even hits from 20 mm cannons. Perhaps most disturbing was the observation that damaged Thunderbolts displayed extraordinary resilience. Despite sustaining severe battle damage, these aircraft could remain in the fight, often limping back to base in England with their wings partially torn or missing, engines streaming oil, and control surfaces shredded or shot away, yet they still remained under the pilot's command. Such durability was starkly different from German fighter aircraft, which typically could not continue flying after comparable damage. When Lieutenant Roach's intact Thunderbolt finally rolled to a halt at Karpik, a small Luftwaffe airfield, the German pilots finally had the opportunity to examine without haste the sturdy aircraft they had long underestimated. The local Luftwaffe personnel immediately recognized the strategic importance of capturing a fully intact and undamaged example of this American fighter. To prevent sabotage or any potential damage during the examination, the aircraft was quickly surrounded by armed guards, their vigilance aimed at securing the valuable asset. In a swift effort to conceal its identity while analyzing the aircraft's performance and construction, American markings were covertly painted over. The Germans replaced the American insignia with their own Luftwaffe markings, specifically the Balk-Crower symbols on the wings and fuselage, and painted bright yellow on the undersurfaces and tail to ensure clear identification in future flights. This bright yellow was not merely aesthetic but was part of standard Luftwaffe practice, identified by the RLM-04 code, to help prevent friendly fire incidents among anti-aircraft defenses and fighter units. Soon after the capture, arrangements were made to transfer the Thunderbolt to Recklinghausen, Germany, where the Luftwaffe's elite testing and evaluation center was situated, roughly 100 kilometers northwest of Berlin, in the state of Mecklenburg. The aircraft was assigned a new designation, T9+FK, following the coding conventions of the Luftwaffe's Zirkis Rosarius Evaluation Unit, which specialized in analyzing captured Allied aircraft. The task of conducting the initial and extensive evaluation flights was entrusted to Hans Vera Lira, a distinguished test pilot and chief engineer at the air testing facility. Lira was a seasoned aviator who had flown over 125 different aircraft types during the war without ever being involved in a crash or experiencing serious damage. Approaching the P-47 with professional curiosity and a critical eye, he was cautious yet eager to uncover the aircraft's true capabilities. His first assessment, meticulously documented in his logbook and later detailed in his memoirs, titled Luftwaffe Test Pilots Flying, reflects a blend of respect for the machines, resilience and a keen analytical interest in its design and flight characteristics. During World War II, examining the formidable aircraft of the Allied forces revealed how advanced and complex their technology had become. The cockpit of these fighters, particularly on the American side, showcased a level of sophistication that seemed to surpass their German counterparts in many ways. What immediately caught a new pilot's attention was the sheer density of gauges and indicators on the instrument panel, which appeared to be roughly double the number typically found in German fighters of the era. This abundance of dials, switches, and levers reflected an intricate array of systems designed to enhance the aircraft's performance, safety, and versatility. Some controls on the American aircraft were unlike anything seen in German designs. Strange levers and switches managed functions that had not been encountered before in Luftwaffe fighters. Notably, the turbo supercharger system demanded an understanding of exhaust flow management that, to German engineers, might have initially seemed purely theoretical. Yet, in American practice, this knowledge was standard rather than experimental, contributing significantly to the aircraft's incredible power output at high altitudes. The process of operating the variable pitch, or constantly adjustable speed, propeller also differed markedly from the simpler systems employed in German fighters. What puzzled many, including seasoned pilots, was the aircraft's elaborate automatic engine management system. German aviators often relied on manual adjustments, constantly tweaking throttle and mixture controls to optimize performance. Conversely, the American design incorporated a complex automatic system intended to simplify the pilot's workload during combat, though its intricacies could initially seem mystifying to even experienced pilots. Leers, a test pilot and engineer, recounted in his memoirs that the cockpit of the P-47 Thunderbolt could seem overwhelming to someone unfamiliar with it. In his words, the P-47 cockpit could baffle even an experienced pilot. Despite this, he quickly began to unravel the functions of many of the instruments and controls. Still, some levers and switches remained obscure at first glance. Recognizing the importance of understanding all systems, he dedicated considerable time on the ground to experimenting with the controls, carefully studying the layout and sequencing before even attempting a flight. This meticulous approach reflected his methodical nature, demonstrating a focus on safely familiarizing himself with unfamiliar aviation technology without the benefit of detailed pilot manuals or operational documents. The starting procedure of the engine alone revealed a level of technological sophistication uncommon among German aircraft. The Pratt & Whitney R2800 Double Wasp, a remarkable 28-cylinder radial engine powering the Thunderbolt, required precise procedural steps to bring the enormous turbo supercharger into optimal operation. Leers approached this process systematically, mentally cataloging each step, rationalizing the purpose behind each motion. When the engine roared to life, its deep, rumbling sound was unmistakably different from the sharp bark of German inline engines or even the BMW 801 radial powering the Focke-Wulf FW190. This powerful, resonant noise spoke directly of its large displacement and considerable torque, hinting at formidable power reserves kept in check until needed. As he taxied the aircraft, Leers carefully felt the weight and inertia transmitted through the controls, conscious of the aircraft's size and mass. The P-47D was a notably heavy single-seat fighter. Its empty weight approached 10,000 pounds, and even this particular example, which carried a substantial amount of fuel and a full complement of ammunition, tipped the scales to nearly 13,500 pounds. Placing this in perspective, the German FW190A8, one of its heaviest and most formidable single-engine fighters, had an empty weight of around 7,650 pounds and a maximum loaded weight close to 10,800 pounds. The size and mass of the Thunderbolt were genuinely impressive, larger than some twin-engine aircraft operated by the Luftwaffe. With the throttle advanced for takeoff, the differences in engineering philosophy between American and German aircraft became immediately evident. The R2800 engine produced roughly 2,000 horsepower under standard boost, with wartime emergency power boosting this figure to approximately 2,300 horsepower thanks to the application of water methanol injection. These power levels were extraordinary for a single-engine fighter at that time. In comparison, the German BMW 801D radial engine, considered one of the finest of its class, delivered about 1700 to 1730 horsepower at its maximum continuous power. While the BMW engine's power output was substantial and well proven in combat, Lears noticed that the Thunderbolt's far greater weight meant its takeoff run was longer than expected, requiring more runway to achieve the necessary speed for a safe departure. The large mass, combined with the powerful engine, emphasized the design philosophy of American aircraft: larger, heavier, yet capable of generating tremendous thrust and power, often pushing the limits of available takeoff distances. The grass-covered surface of the transfer airfield stretched out beneath him as Lurch prepared for takeoff. Once airborne, however, a different reality began to unveil itself, one that challenged his previous assumptions about the formidable Thunderbolt and the risks that German pilots had entirely misjudged regarding the aircraft's true capabilities. As the aircraft ascended steadily, Lurch diligently monitored and nursed the turbo supercharger, ensuring it reached optimal operating temperature, a crucial step as the plane climbed higher into the sky. Below 15,000 feet, the P-47 had seemingly confirmed everything the German fighter's combat reports had claimed. It was heavy and sluggish in tight turns, clearly lacking the agility needed to match nimble enemy aircraft, especially the sleek fighters like the FW-190 and Bf-109. Its rate of climb was mediocre at best relative to these fighters, and any experienced German pilot who found himself in a sustained turning battle at those altitudes would easily outmaneuver the American aircraft with just a bit of skill and patience. Yet, at elevations exceeding 20,000 feet, the character of the Thunderbolt was transformed, revealing a new, astonishing facet of its design and performance. This dramatic change was driven by the turbo supercharger, a remarkable piece of engineering powered by exhaust gases that became increasingly efficient at higher altitudes, where the surrounding air grew thinner. Instead of struggling for oxygen as German engines did, the R-2800 retained its full-rated power capabilities. As the aircraft ascended to about 25,000 feet, the engine continued to deliver full power, whereas German fighters often produced only around 70% of their sea-level output at such heights. In that rarefied atmosphere, Lurch advanced the throttle, pushing it forward at 25,000 feet, and immediately felt the aircraft respond with a surprising burst of acceleration, especially for a machine of its size and weight. It wasn't just climbing, it was surging forward with a vigor that seemed almost reckless given the large silhouette of the plane. Curious, Lurch executed a steep dive to examine its high-speed handling, and what happened next bordered on shock. The Thunderbolt responded with an aggressive enthusiasm, accelerating past 500 miles per hour, a velocity that compressed the airflow dramatically against the airframe, stiffening the controls and making recovery from such a dive a physically demanding task. Both hands gripped the control stick tightly, and the strain on his muscles grew as the airplane approached the limits of its compressibility, a phenomenon that engineers and pilots would not fully understand until the jet age dawned. Lurch was particularly struck by the aircraft's roll rate, which defied all expectations grounded in the knowledge of its weight and size. Despite the heavy appearance and bulk, it could rotate on its axis faster than any of the German fighters Lurch had flown, including the renowned FW-190, which was considered an aerobatic marvel among fighters of its era. This unexpected agility, combined with its incredible dive speed, conferred a distinct tactical advantage. If a high-altitude encounter turned sour, an American pilot could simply roll inverted, then dive away at extremely high speeds, speeds that any German fighter would struggle to match, especially as engine performance continued to drop with altitude. Any Luftwaffe pilot attempting to pursue would soon encounter the effects of compressibility, the rapid decrease in air density that causes significant control issues at ultra-high speeds. The Thunderbolt's robust airframe and the effectiveness of its control surfaces were better equipped to handle these effects than German aircraft, lending the American fighter a further edge in those critical moments. Lurch took advantage of this newfound understanding by systematically flying the captured Thunderbolt through a comprehensive test program, meticulously surveying its flight envelope. Following standard evaluation procedures, he explored its limits, capacities, and performance characteristics in detail. His preliminary report contained observations that unsettled Luftwaffe officials, who held onto the conviction that German fighter aircraft were fundamentally superior in all aspects. Instead, these findings painted a picture that was much more complex and, in some cases, counterintuitive, revealing that the American P-47 Thunderbolt was not merely a tank-like brute but rather a highly capable, dynamically versatile aircraft, especially at high altitude, challenging the deeply held perceptions of the German fighter design's overall supremacy. Soared that dramatically increased the engine's power output at high altitudes. This advanced turbo supercharging system, meticulously engineered and flawlessly integrated, gave the American aircraft a significant edge where German fighters often faltered, a crucial advantage in the increasingly contested aerial battles above 25,000 feet, where the battle of air superiority was often decided. In these lofty heights, where gas contention and maneuvering agility were vital, the P-47 Thunderbolt demonstrated its superiority over German fighters, not by sheer agility but through specialized performance enhancements. It was engineered to excel in high-altitude combat, effectively nullifying the German fighter's traditional advantages in climbing and turning performance. This was a result of intensive design efforts and dedicated testing, aimed at exploiting every capability that American aerospace technology could offer. In the following weeks, Reikland's dedicated engineering team undertook comprehensive examinations of the Beetle engine, following the most rigorous and precise procedures established by renowned Arab standards. They meticulously documented every component, capturing detailed photographs from multiple perspectives to ensure no detail was overlooked. Each dimension was measured with advanced precision instruments, allowing for exact comparisons. All the major components, whether engines or structural parts, were carefully weighed to assess manufacturing consistency and quality control. Systematic tests were conducted under various simulated operational conditions, exposing each part to stresses and extremes, as they would experience during combat. Special attention was devoted to the turbo supercharger system itself, as this technology represented the fundamental distinction between American high-altitude performance and the German approach. The engineers' findings from the meticulous disassembly and analysis of this system revealed results that stunned the American team, who were seasoned in resource-constrained design philosophies typically typical of wartime Germany. The core of the Beetle engine was a Pratt & Whitney R2800 double wasp, a marvel of piston engine engineering consisting of 18 cylinders arranged in dual rows of 9 around a single central crankshaft. The engine's total displacement was measured at roughly 2,845 cubic inches, equivalently about 45.958 liters. For comparison, the German BMW 801D engine displaced about 2,560 cubic inches, or approximately 41.88 liters. However, simply comparing displacement did not illuminate the full picture of their performance differences. Power output and efficiency depended on myriad other factors beyond volume alone. The R2800 engine incorporated forged aluminum alloy pistons, enhanced with sodium-cooled exhaust valves designed to withstand extreme operating temperatures, ensuring durability and consistent performance under demanding conditions. Its crankshaft was a forged component from high-grade steel alloy, materials so sophisticated that German metallurgists, observing their craftsmanship, felt both awe and envy, recognizing that such materials could no longer be readily sourced by their own country. The quality of American materials, combined with the precision of manufacturing processes, was so advanced that it left the German inspection team visibly impressed. Every part of the engine, from the smallest fastener to the major assemblies, reflected extraordinary precision, produced within tight tolerances that ensured optimal performance and reliability. Surface finishes across all components were uniformly smooth, a testament to meticulous finishing techniques that reduced wear and stationary friction. The magnetos, essential for reliable ignition, used materials becoming increasingly scarce in German aircraft, further emphasizing the resource advantage of American manufacturing. The spark plugs employed high-grade ceramics with superior insulating properties, surpassing German equivalents in durability and heat resistance. The fuel injection system, crucial for precise air-fuel mixture delivery, functioned with an accuracy that German engineers might have expected only within a laboratory setting, not in combat aircraft subjected to the rigors of wartime operation. Its flawless operation underscored the American engineers' meticulous attention to detail, with no sign of compromises or substitutions stemming from resource shortages. It was a clear indication that the Americans had replicated the engine exactly as per the original blueprints, utilizing all specified materials, thereby avoiding the downgrades and improvisations that increasingly plagued German wartime production. The turbo supercharger system, the technological centerpiece of the engine, displayed engineering sophistication far ahead of other contemporary aircraft systems. Exhaust gases from all 18 cylinders were meticulously channeled through manifolds that converged and routed the gases via insulated pipes along each side of the fuselage toward a high-speed turbine positioned behind and below the cockpit. The rapid rotation of this turbine, driven by hot exhaust gases, powered a centrifugal compressor that significantly boosted airflow into the engine at high altitudes, greatly improving thrust and performance where German fighters often struggled. This turbo supercharger system was a marvel of military aerospace engineering, engineered with such precise control and integration that it converted the once limiting factor of high-altitude flight into an operational advantage. Germany had attempted to develop similar systems, however, their efforts lagged behind, as they never fully successful in integrating such high-performance turbocharging into production aircraft during the wartime period. The American system, by contrast, was mature, well-tested, and integrated seamlessly into the engine's architecture, contributing substantially to the aircraft's superior high-altitude capabilities. In conclusion, this engine, built with meticulously sourced materials and by the year of 1943, the development of supercharging systems for fighter aircraft had become a focal point of technological innovation, especially given the demanding operational environments in which these aircraft operated. The turbo supercharger represented a significant leap forward, fundamentally altering how high-performance combat planes managed airflow and power at various altitudes. This advanced device, an intricate assembly of components working in seamless harmony, relied on forcing additional ambient air into the engine's intake, drastically increasing the amount of oxygen available for combustion. This process involved the integration of an intercooler, a vital cooling device placed within the system to lower the temperature of the compressed air. By doing so, the intercooler elevated the air density, which in turn allowed the engine to generate greater power without risking the destructive phenomenon known as detonation, which could damage engine components and impair performance. The operation of this system depended heavily on an array of automatic regulators, sophisticated control mechanisms designed to dynamically manage boost pressure as well as the turbine speed. These components were crafted to function without the continuous oversight of a pilot, only requiring the brief adjustment of the manifold pressure setting, a process that could be performed at the ground before takeoff or during non-combat intervals. German engineers, renowned for their precise scientific understanding, had diligently explored similar concepts through an array of experimental programs. They possessed a clear theoretical grasp of the principles underpinning such a system and had even conducted extensive research and small-scale testing to understand its potentials and limitations. Despite these efforts, however, translating this complex theoretical framework into mass-produced, reliable equipment suitable for deployment in frontline aircraft proved daunting. The limitations of German industry, especially by the year of 1943, had become painfully apparent. Chronic shortages of vital materials, coupled with the increasing difficulty of manufacturing to exacting standards amid a strained supply chain, made the mass implementation of turbo-supercharging systems an elusive goal. The key challenge resided in the materials required for the turbine blades. These components needed to withstand, without fatigue or failure, extreme temperatures that could soar above 2000 degrees Fahrenheit during high-speed operation. Raw materials of the required high-performance alloy, variable through the course of the war, were either too scarce or of insufficient quality for mass production. Manufacturing such components demanded unparalleled precision, as minute imperfections could lead to parts cracking or losing aerodynamic efficiency when subjected to the intense forces of operation at high revolutions per minute. The control systems added to this challenge, requiring high reliability and exact calibration to ensure smooth operation across a wide range of temperatures and forces. The ducting system, integral to directing airflow from the intercooler to the engine, was equally complex. It needed to be composed of heat-resistant materials, capable of resisting damage from thermal stress, and assembled with perfect seals to prevent leaks that could compromise the entire system. Every element in this elaborate chain, turbine blades, intercoolers, control units, ducting, had to work flawlessly in extreme conditions typical of combat. Aircraft operating at high altitude faced temperatures around -60 degrees Fahrenheit, yet the same machinery could heat up to over 200 degrees in proximity to the engine or during vigorous combat maneuvers. These conditions, combined with the violent vibration inherent in high-speed flight and the possibility of battle damage, added layers of complexity to the engineering challenge. Despite these obstacles, American industry succeeded in solving every one. They produced, installed, and deemed standard on each and every P-47 Thunderbolt, a formidable fighter aircraft, a turbo-supercharger system that integrated all these technologically advanced elements into a coherent, functioning whole, capable of reliably performing under combat conditions. This turbo-supercharger was not merely experimental or a patchwork solution intended for special missions. It was a core component of the aircraft's design, an integral part of daily operations, and installed in thousands of aircraft, resolutely commonplace and mandated in production lines across American factories. Such an extensive deployment exemplified the capacity of American industry to incorporate cutting-edge technological ideas into mass production seamlessly, a feat that many German engineers struggled to comprehend fully. The widespread use of this advanced device reflected a broader industrial prowess, an ability to produce complex, precise engineering solutions at scale, something that offered significant battlefield advantages. Corresponding assessments by German technical experts, documented through detailed evaluating reports, acknowledged that the turbo supercharger system represented an extraordinarily high level of engineering sophistication. They conclusively noted that the American manufacturing capability had surpassed what German industry could realistically reproduce in large quantities by the year of 1943. The range of technologically demanding processes, using exotic new alloys, executing ultra-precise manufacturing techniques, maintaining rigorous quality control, simply exceeded the strategic material supplies available to Germany at that time. Furthermore, Germany was suffering from the progressive attrition of skilled labor, much of which had been displaced or lost amid the relentless pressure of Allied bombing campaigns. The combination of material shortages and declining manufacturing standards severely constrained their ability to undertake a comparable system on such a large scale. Turning to armament, the American approach demonstrated a similar pattern of abundant resources and meticulous attention to detail. Compared to the infamous German fighter aircraft, notably the Focke-Wulf FW-190A, which was typically armed with machine guns totaling around 2,000 rounds and cannons with a total capacity of approximately 500 rounds, the American P-47 Thunderbolt offered a vastly superior rate of sustained firepower. A pilot flying the P-47 could, in theory, activate all 8 of its heavy guns simultaneously and maintain fire for nearly 20 seconds before running out of ammunition, as the combined fire rate approached 100 rounds per second. When these 8 guns were finally tuned to converge on a single point in space, an art known as harmonization, the resulting volume of destructive fire was virtually overwhelming to any adversary. The effectiveness of this formidable armament was not merely theoretical. German engineers and military testers, after examining captured examples of the aircraft's weapon systems, documented their destructive impact. The level of craftsmanship and installation precision impressed the German experts, who noted that each gun was carefully mounted to ensure reliability and performance. An important aspect of this armament system was the ingenious method of maintaining operational functionality at high altitudes where temperatures could plummet to 60 degrees below freezing. Each gun was housed in a bay equipped with electric heating to prevent the weapon components from freezing solid, thereby avoiding malfunctions during icy combat conditions. Meanwhile, spent cartridge cases and fragments of disintegrating belt links were safely channeled away through chutes that led to ports situated on the lower surface of the wing, a design feature that prevented debris from damaging the aircraft's surfaces or snagging on control surfaces, which could jeopardize flight stability. Throughout testing phases, specifically during the VLAN trials, the weapon system demonstrated exceptional reliability. Thousands of rounds were fired under diverse atmospheric and environmental conditions without a single instance of jamming or feed failures. Furthermore, the quality of ammunition itself highlighted the high standards of American industrial capability. The .50 caliber rounds were produced with armor-piercing cores built to strict, consistent specifications, incendiary compounds designed for reliable performance, and tracer elements that burned at a predictable rate. Such meticulous manufacturing ensured dependable operation in combat. Testing also revealed a noteworthy advantage. American ammunition consistently outperformed German equivalents, which had suffered declines in quality due to shortages of strategic materials amidst the ongoing conflict. The Thunderbolt's armor protection further exemplified American priorities, reflecting a willingness to accept substantial weight penalties in exchange for enhanced pilot survivability. This approach contrasted sharply with German design philosophy, which favored lighter aircraft performance often at the expense of comprehensive armor. The cockpit was enveloped in thick armor plating on multiple sides, forming what American designers called an armored bathtub that safeguarded the pilot from blows from below and behind. The windscreen was constructed from reinforced bulletproof glass capable not only of halting machine gun rounds but also of resisting fragments from exploding cannon shells. Additional armor plates shielded sensitive systems such as the oil coolers and the turbo supercharger, components critical to aircraft operation yet vulnerable in combat. Overall, the armor added up to a weight exceeding 200 pounds, roughly the equivalent of installing 2 extra machine guns with their full ammunition loads. Comparing this to German fighters of the same era, which often carried only minimal armor to preserve speed and maneuverability, it became clear that the American approach prioritized pilot protection more heavily, accepting the performance trade-off as a necessary measure to ensure that pilots had a fighting chance in dangerous encounters. Perhaps the most noticeable difference stemming from this design philosophy was the approach to aircraft maintenance and accessibility. American engineers clearly anticipated that mechanics stationed at forward airfields would need to perform rapid repairs, sometimes under the cover of darkness, adverse weather conditions, or even under threat of enemy attack. As a result, every major component of the aircraft could be accessed conveniently through large panels that were secured with fasteners designed for quick removal, facilitating swift servicing under combat conditions and enabling the aircraft to return to the fight with minimal delay. During World War II, American aircraft engineering principles emphasized practical design features that allowed for rapid, straightforward maintenance in the field, often requiring only simple tools and minimal effort. For instance, major engine changes on these aircraft could be accomplished within a span of just a few hours, utilizing standard hoisting equipment and following well-documented, straightforward procedures that ensured efficiency and reduced downtime. In contrast, German fighters, which were fundamentally designed with an expectation of complex, factory-level repairs, generally demanded much more extensive disassembly for significant maintenance or major component repairs, owing largely to their more intricate construction. This notable difference in design philosophy largely reflected the contrasting resource realities of the two nations. American industry, characterized by its abundance of materials, manufacturing capabilities, and engineering resources, prioritized maintainability and operational readiness in their aircraft designs. American engineers were free to optimize their aircraft for ease of maintenance, focusing on creating models that balanced performance with practicality, rather than solely maximizing manufacturing efficiency. This approach resulted in a sense of robustness and serviceability that often outstripped their German counterparts. Furthermore, American technological advancements manifested vividly in the aircraft's communication systems, as exemplified by the communications equipment installed in the captured P-47 Thunderbolt. This aircraft was equipped with an SCR-274N command radio capable of air-to-air and air-to-ground communication, along with an SCR-515 a liaison radio, providing an array of additional communication channels. Both of these radios exerted superior clarity and had a greater operational range than the contemporary German systems, which frequently suffered from persistent interference issues. American engineers had effectively addressed these problems through superior design choices, employing higher quality components and improved shielding techniques, resulting in both clearer signal transmission and more reliable communications. Moreover, these communication systems integrated with an advanced identification mechanism, often termed friend or foe, or IFF system. This technology automatically identified Allied aircraft to ground controllers and other units, significantly reducing the risk of friendly fire incidents. Such automated identification features appeared to be at a level of sophistication that the German forces had not yet achieved in 1943, highlighting the technological gap between the two nations' aircraft designs. Perhaps the most striking aspect for German engineers studying such captured aircraft was not any individual advanced feature but rather the overarching impression of impeccable quality and completeness observed throughout the entire aircraft. Every component seemed to represent the pinnacle of American engineering, manufactured to the highest standards, using the best materials available, and with meticulous attention to detail. There were no visible signs of compromises that might have arisen from material shortages or resource constraints. No parts appeared to be hastily substituted with inferior materials in place of preferred ones, nor were there the desperate improvisations that increasingly marked German wartime production. As Allied strategic bombing campaigns devastated German industrial capacity and resource shortages intensified, German aircraft maintenance and production became progressively more compromised. In fact, German technical reports, such as those compiled at Rechlin and disseminated through Luftwaffe technical channels, consistently underscored this point, emphasizing that the P-47 Thunderbolt was constructed in strict accordance with its original design specifications. These reports stressed that the aircraft was assembled using all intended materials and processes, with no evident compromises arising from shortages or operational constraints. Maintaining this level of manufacturing fidelity to the original design became an arduous challenge for German industry. As the war dragged on, reflecting the broader struggles faced by their wartime economy. Throughout late 1943 and into the early months of 1944, the ongoing flight testing of captured P-47s provided valuable comparative data. Additional aircraft, seized by German forces, were carefully evaluated at Rechlin, allowing engineers to analyze the tangible differences in manufacturing quality, resilience, and overall design integrity. On the 29th of May, 1944, another P-47 found its way into German hands after an incident involving 2nd Lieutenant Lloyd S. Hathcock from the 3001st Fighter Squadron, part of the 332nd Fighter Group. Lieutenant Hathcock's disorientation during his mission resulted in his aircraft ultimately being shot down or forced to make an emergency landing, leading to its capture by German forces. Imagine a scenario where an American fighter aircraft, in the chaos of a routine ferry flight, mistakenly drifts into enemy territory and unexpectedly lands at a hostile airfield, in this case, the Rome Littorio airfield in Italy, which was under German control. The aircraft involved, with the serial number 427591, was swiftly captured by German forces before the pilot could regain control or attempt a rescue. This particular P-47 Thunderbolt, renowned for its formidable presence in the skies, had once been the personal mount of a renowned American ace, George Notney, credited with claiming 8 aerial victories while serving with the 317th Fighter Squadron. The significance of this aircraft extended beyond its combat record, as its capture and subsequent testing provided critical insights for the Germans. After seizing the aircraft, the Germans transferred it to their facilities in Wrexham, where it was initially assigned the designation 8 and 6. Later, on October 12 of the year 1944, the aircraft was moved into the possession of Zirkis Rosarius, a special Luftwaffe unit responsible for testing and analyzing captured Allied aircraft. Under this program, the aircraft was given a new identification, a combination of letters and numbers, specifically T9LK, marking it as part of a fleet of test aircraft enhancements and evaluations. The data collected during testing at a location called Rechlin proved invaluable. It resulted in tactical recommendations for German fighter pilots operating in the skies over Europe. These reports advised that engaging P-47s below the altitude of 15,000 feet maximized the probability of success for German fighters. This tactic was rooted in analyzing the Thunderbolt's operational shortcomings, its subpar performance at low altitudes and its sluggish rate of climb. These characteristics naturally gave German fighters, which could maneuver and accelerate more effectively in the same regime, a crucial advantage. German pilots were, in particular, cautioned against trying to evade attacks by diving away from P-47s. The American fighters could, when threatened, accelerate rapidly to velocities that German aircraft struggled to match while diving. This indicated that aggressive, focused attacks with concentrated firepower were necessary rather than hasty attempts to escape or presume that a few damaging hits would bring down the Thunderbolt. Furthermore, the reports emphasized that even when damaged, P-47s frequently continued to display resilience and mobility that sometimes surpassed expectations. Despite sustaining extensive battle damage, these aircraft often maintained flight, persevering where German fighters might have been forced to break off or break apart. This durability under fire reinforced the importance of persistent and aggressive engagement strategies, rather than conservative tactics that might prematurely abandon the attack. However, these tactical advices, while useful for individual pilots' battlefield decisions, could not alter the core strategic issues facing the German forces. The vast material superiority of the Allied forces rendered these tactical adjustments somewhat superficial in the face of an overwhelming industrial and logistical powerhouse. The Americans produced and replenished aircraft at a staggering rate, at one point, exceeding 300 new P-47s every month. This relentless flow of aircraft assured that every Thunderbolt damaged or destroyed was quickly replaced, eroding the German advantage. Concurrently, American pilot training programs continued to churn out highly skilled aviators in ever-increasing numbers, further tilting the battlefield balance. In stark contrast, German training had been compressed due to wartime pressures, and fuel shortages frequently constrained operational hours. Meanwhile, the logistics systems that supported American aircraft, delivering fuel, ammunition, and spare parts, functioned efficiently and without significant interruption, even amidst intense Allied aerial assaults. German logistics, on the other hand, suffered heavy attrition under relentless Allied attacks, gradually breaking down under the sustained pressure. The captured P-47s eventually found their way into the hands of the Wunderschuss Rosarius, a specialized Luftwaffe demonstration unit commanded by the distinguished Captain Theodor Rosarius. This unit played a key role in operational psychological warfare and intelligence gathering by visiting frontline fighter bases across occupied Europe. The purpose of these demonstrations was twofold: to educate German pilots by familiarizing them with the appearance and tactical features of enemy aircraft, and to serve as psychological warfare tools by showcasing the weaknesses and strengths of Allied technology. During these visits, German pilots could see firsthand the physical characteristics that distinguished American Thunderbolts from German fighters. They observed details such as wing shapes, fuselage contours, and distinctive markings, enabling quicker and more accurate recognition in combat conditions. More importantly, they learned about the operational capabilities of these aircraft, including their high-altitude performance and combat tactics. These demonstration flights often revealed a sobering reality: that Allied aircraft, exemplified by the captured P-47s, were often technologically superior in certain crucial areas. Especially at high altitudes, where air combat increasingly centered late in the war, the American Thunderbolt demonstrated capabilities that German fighters struggled to match. The physical evidence of the aircraft's robustness, speed, and altitude performance left a lasting impression on the German pilots who attended these displays. Interviews conducted with Luftwaffe American fighter aircraft capabilities were demonstrated directly and irrefutably through a series of combat tests and intelligence assessments. While pilots of the Zirkis Razarius unit were able to show that German fighters retained certain advantages in specific flight regimes, particularly at medium altitudes, the overall picture that emerged from these demonstrations made it clear that at the higher altitudes where most American bomber fleets operated, the German fighters found themselves at a significant and growing disadvantage. Analyzed intelligence obtained from captured P-47 Thunderbolts included detailed performance data that directly challenged some of the overly optimistic assumptions circulated within Luftwaffe briefings earlier in the war. When examined closely, these figures revealed the true capabilities of the American fighters. At sea level, for instance, the P-47D model achieved a top speed of around 350 miles per hour. A respectable figure, but not particularly impressive when compared to the German FW-190A, which could reach approximately 408 miles per hour at the same altitude. Moving to 10,000 feet, the Thunderbolt's maximum speed increased to roughly 375 miles per hour, demonstrating the expected performance gain with altitude. However, at 30,000 feet, the difference became stark. The P-47D could reach about 426 miles per hour, whereas the Focke-Wulf FW-190 struggled in comparison, struggling to hit 370 miles per hour, and the Bf-109G model managed only around 385 miles per hour. This performance margin at operational combat altitudes was not just noticeable, it was decisive and continued to grow more critical as Allied bombing missions correspondingly increased their flying height to minimize damage from German anti-aircraft artillery. The comparison of service ceilings provided another disappointing insight for German pilots. The P-47 Thunderbolt could reach altitudes of up to 42,000 feet, a ceiling that German fighters rarely approached in actual combat, as their effectiveness rapidly declined above approximately 35,000 feet. The thinning atmosphere at higher levels caused a significant reduction in the power output of the German engines, severely limiting their fighters' operational capabilities and maneuvering effectiveness at these extreme heights. In contrast, American bomber and fighter formations could, and frequently did, operate at altitudes where German interceptors struggled merely to reach them, or when they did arrive at these heights, they were hindered by insufficient power reserves and capabilities for effective combat maneuvers. The P-47 escorts, with their turbocharged engines, maintained full combat efficacy and agility at these high altitudes, whereas German fighters often found themselves outpaced and outmaneuvered, grappling with declining performance. Further illustrating American technological and logistical advantages, range comparisons between American and German fighters revealed a significant disparity. The P-47D, especially when equipped with external wing tanks, could escort bombers flying deep into enemy territory. While early models of the P-47 had more limited range that curtailed their operational flexibility, by 1944, Thunderbolts fitted with 108 drop tanks routinely completed patrols covering 1,000 miles or more. This capability starkly contrasted with German fighters, which were primarily designed for short-range, point defense missions, such as intercepting threats close to the Reich's borders. Their internal fuel capacities did not support extended operations, forcing them into a defensive posture. This operational radius gap meant American fighters could choose when and where to engage, often inserting themselves into enemy airspace for pre-planned missions or to intercept incoming formations, while German fighters were largely confined to defensive operations, limited by their fuel constraints and lower endurance. Captured Thunderbolts also provided valuable insights into American pilot training, tactical doctrine, and combat philosophy. Examination of gun camera footage, along with analysis of the damage patterns on aircraft that had survived combat before falling into enemy hands, collectively suggested that American pilots consistently relied on tactics that maximized the strengths of the P-47, operating predominantly at high altitudes where the turbo-supercharger's advantages could be fully utilized. These pilots skillfully maintained formations and engaged enemies at ranges and altitudes that played to their aircraft's superior performance in those conditions, while tactically avoiding situations that would expose the fighter's vulnerabilities. In summary, the extensive evidence from direct demonstrations, captured aircraft, and post-mission analyses painted a clear picture. The American fighters, especially the P-47 Thunderbolt, had been engineered and employed in a manner that allowed them to dominate the skies at decisive points in high-altitude combat. Their speed, altitude ceiling, endurance, and adaptability gave them a strategically advantageous edge over German fighters, which struggled to keep pace due to technical limitations and tactical restrictions. This systemic superiority played a crucial role in shaping aerial combat outcomes and ultimately contributed significantly to the Allied air campaign's success. During the air battles of the war, Allied pilots preferred to adopt hit-and-run tactics, frequently employing dive and zoom attacks rather than engaging in the drawn-out, turn-and-fight dogfights where German fighters generally held the upper hand. These pilots operated mainly in coordinated pairs or in formations of 4 aircraft, meticulously supporting each other rather than engaging in solo battles where individual bravado might tempt a pilot to break from the collective strategy. Even when isolated opportunities for individual combat appeared promising, they often chose to maintain formation integrity, demonstrating a disciplined approach built on teamwork and tactical discipline. This meticulous coordination and adherence to strategic principles did not go unnoticed. Analysts from the German Air Force, known as the Luftwaffe, carefully examined the available evidence from aerial combat reports and found themselves continually impressed by the degree of discipline shown by American pilots. Unlike many German aces, who often preferred to rely on their personal skill, aggressive tactics, and individual daring to secure victory, American pilots committed themselves to a unified doctrine. They adhered to structured formations, supported their wingmen systematically, and avoided the pitfalls of overconfidence or reckless individuality that might jeopardize the team's effectiveness. The combination of this carefully practiced discipline, access to better high-altitude reconnaissance and combat equipment, and the increasing numerical superiority of Allied forces created a formidable advantage that even veteran German pilots found increasingly difficult to counter as the war wore on. By the time of the D-Day invasion in June of 1944, the strategic environment had shifted so deeply in favor of the Allies that any intelligence derived from captured aircraft offered little practical benefit or strategic insight to Germany's desperate war effort. The Luftwaffe, despite its experience and tactical knowledge, was aware of several critical realities. They conceded that Allied equipment was generally superior in many key technical aspects. Their intelligence sources revealed detailed information about American tactics and strategies. They had access to comprehensive technical data concerning the performance of Allied aircraft, which underscored the technological edge held by the Allies. However, possessing this knowledge proved insufficient in counteracting the vast resource disparity between the opposing sides. Germany lacked the necessary quantity of strategic materials, industrial capacity, advanced manufacturing technologies, and adequately trained personnel to match the Allies' growing industrial and military output. The detailed reports, such as the Rechlin compilations, meticulously prepared and circulated among Luftwaffe technical bodies, served mostly to underline and document the expansive technological and industrial gap that increasingly drove Germany toward inevitable defeat. A stark illustration of that gap lay in the production capacity for aircraft engines. American industry, led by companies such as Pratt & Whitney along with the Ford Motor Company, had produced over 125,000 of the R-2800 engines by the end of the war. This single engine type alone, the R-2800, surpassed the total combat aircraft engine production of the entire German war effort. In comparison, BMW produced roughly 61,000 units of their 801 radial engine throughout the entire conflict, a figure that falls dramatically short of American output. Germany's most produced inline engine, the Daimler-Benz DB605, was manufactured in approximately 42,400 units over many years, a far cry from what American factories achieved with fewer resources. In fact, the production of one highly advanced American engine, the Pratt & Whitney R-2800, exceeded Germany's entire combined output of combat aircraft engines across all its models of the war. Furthermore, the scale of American aircraft production vividly illustrated this vast industrial gap. In 1944 alone, American factories produced roughly 96,000 aircraft, whereas Germany managed to produce only about 25,000 of all types combined. These totals included 38,000 fighters, 16,000 heavy bombers, and thousands of medium bombers, transports, and training aircraft. When considering the broader Allied effort, comprising British and Soviet industries alongside American output, the advantage in aircraft production grew even more pronounced, surpassing a ratio of over 5-to-1 by mid-decade. The industrial infrastructure supporting this extraordinary output was unrivaled. For example, the Aluminum Company of America, known as Alcoa, produced more aluminum in a single year than the entire German aluminum industry could generate over the entire course of the war. Similarly, the American steel industry had scaled up to extraordinary levels, ensuring the manufacturing of the vast quantities of materials necessary to sustain aircraft and armaments production on a phenomenal scale. Through these combined efforts, the Allied powers developed an overwhelming material, technical, and logistical superiority, an advantage rooted in the immense scale of their industrial economies that Germany simply could not match despite its technological prowess. Throughout the war, American industry overwhelmingly outproduced entire regions of Europe's industrial landscape, demonstrating a relentless capacity for manufacturing scale and technological advancement. The factories dedicated to constructing vehicles and machinery operated with remarkable efficiency, often utilizing moving assembly lines, a method pioneered by German plants, yet perfected and exploited by American industries to unprecedented levels. Even the machinery producing the tools necessary for manufacturing complex aircraft was produced in such vast volumes that the United States was able not only to supply its own military needs but also to send substantial quantities of equipment to bolster the efforts of British and Soviet allies. This level of production capacity meant that American war efforts were backed by an industrial might whose scale was almost hard to comprehend. Among the many aircraft that embody this industrial supremacy were the P-47 Thunderbolt fighters, some of which were captured in the final, chaotic months of the European conflict. One notable example, officially designated T-9+FK and originally known as William Roach's Beetle, was recovered by American forces at the Göttingen airfield in May of the year 1945. It was found among a collection of captured Allied aircraft, which the Germans had been systematically evaluating as part of their intelligence and technological assessment efforts. Photographs taken by American troops depict this particular Thunderbolt still bearing remnants of German markings, parked alongside German-built FW-190s and Bf-109 fighters, an arrangement that, in effect, resembled a makeshift museum showcasing the full range of captured equipment. This collection served not merely as a display but as a tangible testament to the quantity and diversity of German efforts to analyze their adversaries' technology. The Thunderbolts used by German evaluation units provided German pilots and engineers with an urgent learning opportunity, an education that they desperately needed but received too late to influence the strategic course of the war significantly. These aircraft exemplified a core aspect of American industrial philosophy during the conflict: the prioritization of total capability over elegance or refined efficiency. The approach relied heavily on abundant resources, systematic mass production, and a focus on maintaining an overall material advantage, rather than meticulously tailoring each component for optimal performance. This philosophy, when implemented with nearly limitless materials and manufacturing capacity, yielded weapons systems that, in aggregate, surpassed their German counterparts even when those German designs boasted superior specific features in isolated technical parameters. The lessons imbued by this manufacturing and engineering philosophy extended far beyond individual aircraft models like the P-47. Every piece of captured American equipment told the same fundamental story. For example, the B-17 Flying Fortress bomber, equipped with 4 turbo-supercharged Wright Cyclone engines, exemplified a strategic bombing capability that Germany had consistently failed to develop domestically. Similarly, the P-51 Mustang, famous for its elegant combination of American aircraft design principles with the British Rolls-Royce Merlin engine, stood as perhaps the most exemplary piston engine fighter of the entire war, praised for its speed, range, and agility. Another example was the P-38 Lightning, which demonstrated American willingness to experiment with unconventional solutions, featuring twin-turbo supercharged engines and a tricycle landing gear, a departure from traditional fighter configurations. Each aircraft, regardless of its specific role, consistently reflected a core American tactic: addressing complex aviation challenges through superior engineering, supported by a vast industrial capacity, rather than through cleverness constrained by limited resources. This approach was clearly evident in the observations of Luftwaffe analysts, who soon realized that their enemies were not primarily defeating them through superior tactics or better trained pilots, though American pilot training programs were producing large numbers of capable aviators. Instead, the Germans understood that American victories stemmed from an industrial system capable of designing, producing, and deploying adequate equipment in vast quantities. It was this overwhelming industrial system that gradually rendered many of the Germans' qualitative advantages increasingly irrelevant across the battlefield. By employing this philosophy, American designers aimed to build systems that prioritized functionality at scale, focusing their efforts on creating reliable, mass-producible aircraft that could be churned out in enormous numbers. It was an approach rooted in the belief that, with sufficient quantity and industrial resilience, the United States could offset any regional or technical shortcomings. Ultimately, this vast industrial capacity proved decisive, accelerating the Allied victory and setting a new standard in military manufacturing during the 20th century. The industrial strengths of the involved nations played a crucial role in shaping the course of the conflict, with massive manufacturing capabilities, a wealth of raw materials, and streamlined logistical systems providing significant advantages. By the year of 1943, Germany had reached a point where, despite severe limitations on its industrial capacity, it was still engaging in innovative engineering efforts. These efforts aimed to compensate for their diminishing industrial might by developing clever design solutions, demonstrating a deep commitment to maintaining technological relevance amid the worsening circumstances. Throughout this period, the strategic implications of Germany's industrial constraints were meticulously documented and analyzed within the technical branches of the Luftwaffe. As the year ended, Germany possessed arguably the most advanced air force in the world, boasting aircraft that were generally regarded as superior to those of their adversaries on a one-to-one basis. German pilots, benefiting from more thorough training in comparison to many of their opponents, employed more sophisticated tactics, further emphasizing their tactical edge. Nevertheless, the core issue remained. German industry was fundamentally incapable of sustaining these advantages over the long term once faced with the vast industrial resources of their opponents. In the early years of the war, particularly around 1940, Germany's aircraft designs and pilot skill allowed them to frequently outperform American and Allied counterparts. This was especially evident in the year 1942, when German aircraft still retained a degree of superiority. However, by the time the years 1943 and 1944 unfolded, the situation had shifted dramatically. American factories, fueled by relentless industrial expansion, doubled their aircraft production repeatedly. Once in 1940, again in 1941, once more in 1942, and continuing apace into the following years. By 1944, the United States was manufacturing over 96,000 aircraft annually, a level of production that far outstripped Germany, which consistently failed to surpass 40,000 aircraft per year, despite intense efforts to boost its output. This disparity in industrial capacity directly influenced the quality and technological edge of aircraft produced by each side. The chasm between American and German aircraft design grew wider with each passing year. In 1942, German aircraft were occasionally superior to their American opponents in terms of performance and design. Yet, by 1944, American aircraft had caught up and often exceeded German designs in nearly every critical aspect, including speed, armament, range, and durability. Entering 1945, the gap had expanded into an almost insurmountable divide, leaving German aircraft increasingly outmatched by their better resourced enemies. The evolution of American fighters like the P-51H and P-47N exemplified a natural refinement process of already excellent basic designs. These aircraft symbolized an ongoing effort to improve aerodynamics, armament, and endurance, leading to highly capable and versatile fighters. On the other hand, German fighters such as the relatively obscure but desperate TAR-152 represented frantic attempts to extract additional performance from a declining industrial base. German industry was under relentless pressure from strategic bombing campaigns, critical shortages of raw materials, and the need to replace experienced workers with poorly trained forced labor, which collectively hampered ongoing aircraft development and production. The psychological toll of these material and technological disadvantages was profound on Luftwaffe morale. Facing continuous waves of increasingly capable enemy aircraft became as psychologically damaging as the material losses in aircraft and personnel. German pilots, who once saw their roles as honorable combatants, increasingly perceived themselves as targets in a relentless, systematic destruction campaign. Despite shooting down numerous Allied aircraft, new enemy planes appeared incessantly, creating a frustrating cycle with no end in sight. The inherent numerical superiority of the American forces, driven by sheer volume, logistics, and factory output, ultimately won the day through attrition. No matter how skilled the German pilots were, they could not overcome the relentless tide of American aircraft, which was delivered in far greater quantities daily. The advantage was further bolstered by superior logistics and rapid replacement of lost pilots and planes. This combination fostered a pervasive sense of inevitable defeat within the German fighter units during the year 1944, as they observed the overwhelming and increasingly superior strength of their opponents. Concrete evidence of this reality came from captured American aircraft, particularly the formidable P-47 Thunderbolt. These aircraft were tangible proof, material artifacts that German pilots could directly examine and analyze. The P-47 was not a miraculous weapon nor a revolutionary technological breakthrough, but rather a well-designed, robust, and effective fighter aircraft tailored to its specific operational role. Its success stemmed from careful engineering, high-quality materials, and thorough training, rather than any radical technological innovation. The aircraft epitomized what could be achieved through solid design principles, manufacturing efficiency, and a clear understanding of mission requirements, all of which allowed it to withstand the intense pressures of wartime combat and maintain an edge over less capable adversaries. Power, proper armament, and appropriate protection, all carefully designed and manufactured in vast quantities to ensure overwhelming superiority through the relentless application of material excess. The ultimate irony of history lies in the fact that the Germans, despite mastering these lessons thoroughly, carefully recording their findings with precision and professionalism, and fully comprehending their implications, were ultimately incapable of putting this knowledge into effective practice. Gaining a deep understanding of American industrial dominance did not translate into access to the critical raw materials, such as aluminum, steel, and fuel, or to the skilled labor force, undamaged factories, and fully operational transportation infrastructure that were essential for Germany to produce aircraft on par with those of the Allies in similar volumes. Likewise, knowing the exact performance specifications of the P-47 Thunderbolt did not equip German engineers with the necessary high-temperature alloys, precise manufacturing technologies, sophisticated quality control systems, or the skilled workforce required to produce comparable turbo-supercharger units. The intelligence gathered from the examination of captured aircraft and documented in detailed records illustrated the extent of Germany's defeat with scholarly thoroughness, yet these detailed analyses provided no realistic strategies for avoiding eventual defeat. Their meticulous technical reports, although rich in data, ultimately lacked the means to bridge the gap caused by dwindling industrial capacity. When Allied forces took control of Rechlin and the surrounding facilities in May of 1945, they uncovered extensive archives detailing Germany's aircraft evaluation program. These files were filled with technical reports that meticulously recorded every measurable attribute of both American and British aircraft that had been examined throughout the war. These documents stood as exemplars of methodical and objective scientific research, embodying thousands of hours of painstaking work. They sought to chart every detail, dimensions, performance traits, structural features, a clear testament to Germany's scientific and engineering rigor. However, these reports also revealed a stark truth. While Germany had succeeded in observing and documenting the performance of Allied aircraft in extraordinary detail, they never found a feasible way to replicate this level of capability given the rapid decline of their industrial base. The depth of knowledge contained in these files only underscored the enormous challenge they faced, as the German war effort was increasingly hampered by resource shortages and infrastructural damage. Post-war American technical intelligence teams reviewing these German documents expressed a measure of professional admiration. They recognized that German engineers had developed an understanding of Allied aircraft capabilities that often exceeded the comprehension of American command. German reports highlighted weaknesses and vulnerabilities in American designs, knowledge that experienced American pilots gradually learned to mitigate through their own tactical adjustments and crew training. The level of technical scrutiny in the German evaluations was sometimes even more detailed and rigorous than the Americans' own post-war assessments of their aircraft. This was a reflection, perhaps, of Germany's long-standing tradition of engineering excellence. Yet, in analyzing the broader implications, the American reviewers also saw what these German reports implicitly revealed about Germany's strategic predicament: an attempt to wage a modern industrial war with an industrial foundation already gravely compromised. Germany had tried to rely on excellent engineering, superior pilot training during the early stages of the conflict, and tactical innovation born of immediate necessity to backstop their industrial shortcomings. These advantages had helped them score early victories when facing enemies with similar resource limitations. However, against an opponent like the United States, whose industrial output vastly exceeded that of all other combined powers, the combination of engineering skill and tactical ingenuity was fundamentally insufficient to change the inevitable outcome. The story of German engineers studying captured P-47s vividly illustrates the stark realities of industrial limitations. Despite their intense knowledge and detailed documentation, they could only observe and analyze, powerless to remedy the fundamental deficiencies caused by industrial decay and resource shortages. Their painstaking efforts highlight a sobering truth: the greatest technological and tactical mastery can only delay defeat in the face of overwhelming industrial superiority by an adversary, not prevent it entirely. The evolution of aerial warfare by the time of the Second World War marked a significant turning point in military technology and strategy. Aircraft became not just tools of reconnaissance or reconnaissance-supported artillery, but formidable weapons capable of shaping entire campaigns. Among these, the aircraft known as the Thunderbolt emerged as a symbol, an icon of American industrial ingenuity and military power, rather than merely the ultimate in aerodynamic design or performance. Its prominence stemmed not from being the unrivaled champion across every conceivable metric, but from its combination of effectiveness, durability, and the sheer scale of production, which rendered individual technical advantages ultimately insignificant in the larger strategic picture. During the conflict, American industry produced an astonishing total of over 70,000 fighter aircraft, an achievement that was unmatched in military history to that point. Among these, the Thunderbolt was manufactured in the tens of thousands, with approximately 15,683 units rolled off production lines. This impressive industrial output was paralleled by the simultaneous assembly of even greater numbers of other iconic fighters, such as the P-51 Mustangs, which totaled nearly 15,486, the P-38 Lightnings with just over 10,037, the F-6F Hellcats amounting to 13,738, and the F-4U Corsairs with 12,571 units. This massive scale of production was not merely a testament to American manufacturing capacity, it was an asset of strategic importance. Each aircraft represented countless hours of skilled labor, vast quantities of critical materials like aluminum and steel, and a highly complex network of manufacturing processes and technological capabilities that the Axis powers, particularly Germany, found difficult to match. To German pilots, the P-47 Thunderbolt became a symbol towering over the chaos of war, embodying American industrial dominance and technological resolve. German aviators nicknamed this aircraft the Jug, referencing its somewhat unwieldy appearance and rugged build, which contrasted sharply with the sleekness of some contemporary fighters. They also affectionately called it Indiana, after the Thunderbird insignia painted on many squadron engines, signifying a kind of national pride. As the war progressed and the strategic situation for Germany grew increasingly dire, The relative fame of the Thunderbolt was reinforced by its formidable reputation in combat, an aircraft that inflicted severe losses on German fighters and bombers. German Luftwaffe pilots quickly learned to respect this aircraft, a respect born out of bitter experience. They acknowledged its heavy armament, robust construction, and the dominance it could exert at specific altitudes. They dubbed it that 8-gun fighter, a recognition of its firepower, and learned increasingly to avoid engaging it at high altitudes above 20,000 feet, where the aircraft's turbocharged supercharger gave it a decisive edge. These high-altitude confrontations often proved to be battles of technology and power, with the Thunderbolt leveraging an altitude advantage that was difficult for German fighters to counter, owing to its superior performance in those conditions. By the time the war drew to a close, the impact of the P-47 Thunderbolt was starkly evident in its combat record. It had destroyed approximately 3,752 enemy aircraft in aerial combat, a statistic that underscored its effectiveness in the air-to-air role. Conversely, total losses for the Thunderbolt reached around 3,499 units, an astonishingly balanced exchange, especially considering that from mid-1944 onward, the aircraft was mainly engaged in ground attack missions rather than traditional aerial dogfights. These losses were due to a variety of factors, including operational accidents, mechanical failures, and the hazards of close air support, where aircraft were often exposed to intense anti-aircraft fire during low-level assaults. In its role as a fighter escort during the early years of America's involvement, specifically in 1943 and into 1944, the P-47 demonstrated much more favorable exchange rates, particularly when fighting at high altitudes. This is where its turbo-supercharged engine was most beneficial, allowing the aircraft to excel in defending bomber formations against enemy fighters. However, it was its transformation into a ground attack aircraft that revealed yet another defining aspect of American military philosophy: adaptability and field versatility. As the Allies introduced the P-51 Mustang, which boasted extended range capabilities ideal for long-distance bomber escort, the 9th Air Force began reassigning many Thunderbolt units to tactical air support missions. The Thunderbolt, with its design rooted in rugged practicality, proved exceptionally well suited to such roles thanks to several key characteristics. Its powerful radial engine, which cooled air efficiently and was highly reliable, combined with its heavy armor protection, made it ideally suited for the perilous low-altitude attack missions that typified ground support operations. These same features, factors that contributed to its seemingly ponderous appearance in dogfights, were assets when attacking ground targets. Its considerable size and weight conferred a degree of survivability against small arms and anti-aircraft fire, while its heavy armament made it capable of delivering a destructive punch against fortified positions, railway engines. During the course of their extensive campaigns, the Allied forces reported the destruction of a staggering quantity of German military equipment. Official documentation, supported by corroborative gun camera footage and detailed after-action reports, indicated that the Allies had neutralized over 86,000 railway cars, 9,000 locomotives, 6,000 armored fighting vehicles, and an astonishing 68,000 trucks. While it is inherently impossible to avoid some degree of duplication in such large-scale claim records, the overall magnitude of these figures laid bare the significant toll inflicted upon German logistical and operational capacity. This level of destruction inevitably disrupted the very backbone of German military mobility, forcing the enemy into a state of logistical disarray. In parallel, the multi-role prowess of aircraft like the P-47 Thunderbolt was on full display. Armed with an array of bombs, rockets, and its distinctive 8 machine guns, it had evolved into a versatile and formidable weapon of war, capable of participating effectively in a variety of combat scenarios. Ground forces on the German side came to recognize and dread the unmistakable sound of Pratt & Whitney's R-2800 radial engines when they roared at low altitude. That deep, rumbling sound served as an acoustic warning sign for impending attacks, which German troops found themselves largely unable to prevent or defend against. Over time, the persistent threat from these aircraft, and the material losses they wrought, had a profoundly negative impact. The relentless air assaults, coupled with the destruction of military equipment and the disruption to communications and supply lines, played a measurable role in eroding the combat effectiveness of German ground forces during the crucial years of 1944 and 1945. Turning to the fate of individual aircraft captured by the Allies offers a more detailed epilogue to the broader narrative of aerial warfare. One such aircraft was the P-47D Thunderbolt known as Beetle, bearing the serial number 42-22490, which the Germans designated as T9 and FK. Remarkably, this aircraft survived the conclusion of the war and was recovered by American forces in May of 1945 at a location known as Göttingen. After careful evaluation by American intelligence teams, whose role included scrutinizing German testing procedures, the aircraft was ultimately rendered obsolete and subsequently scrapped. A similar fate befell Lloyd Hathcock's P-47D, numbered 42-75971 and also assigned the designation T9 plus LK. It was recovered but not preserved for historical purposes. The subsequent trajectories of the pilots who flew these aircraft diverged markedly. William Roach, the pilot of Beetle, spent the remaining years of the war confined at Stalag Luft I in Bath, Germany. His liberation came in May 1945 when Soviet forces advanced into the area, and he was able to return to his home country of the United States. By contrast, Lloyd Hathcock faced almost a year of captivity, primarily held at Stalag Luft III, a camp famous for the notorious Great Escape that took place just 3 months before his arrival. His experience was further distinguished by the fact that he was the only African-American pilot among thousands of predominantly white prisoners. When the Germans evacuated the camp in January 1945 as the Soviet advance approached, Hathcock and the other prisoners endured a grueling winter march to the prisoner of war camps at Stalag 7A and subsequently at Stalag 13D. They were liberated by Allied forces in April of that year, shortly before the close of hostilities. Following the war, Lieutenant Hathcock returned to the United States, where he became an influential figure in the nascent effort to desegregate the United States Air Force. His contributions extended beyond integration. He pioneered groundbreaking innovations in aerial reconnaissance photography at Wright-Patterson Air Force Base, significantly advancing the technological capabilities of military intelligence. Another remarkable individual was Hans Vera Lehr, who managed to survive the tumult and chaos of the war despite having flown over 125 different aircraft types during that period. His diverse experience included piloting numerous captured Allied aircraft, making his career essentially a roller coaster of experimentation and reconnaissance. Lee's impeccable safety record, never experiencing a crash or causing serious damage, stands as a singular achievement in the history of aviation, especially given the vast number of aircraft and complex testing environments involved. After the conflict, he provided valuable debriefings to Allied intelligence agencies, offering unprecedented insights into German aircraft development programs. His detailed memoirs, published in the German language in 1977 and translated into English in 1980, remain a vital resource, offering one of the most thorough first-hand accounts of the German efforts to develop, test, and utilize captured foreign aircraft during the war. The examination of captured aircraft such as the P-47 Thunderbolt played a crucial role in shaping the German Luftwaffe's understanding of Allied aerial power during the conflict. The detailed analyses of these aircraft revealed far more than mere technical specifications. They exposed the fundamental strategic realities of the air war that was shaping the outcome over Europe. In the broader context, the story of the captured Thunderbolts at the German-held airfield in Reekland serves as a powerful illustration of how certain technological evaluations transcend mere aircraft performance. These experiences demonstrated that by the year 1943, the decisive factor in the aerial conflict was no longer solely pilot skill, tactical ingenuity, or individual aircraft capabilities. Instead, the ultimate determinant had become the ability of nations to mobilize their entire industrial capacity, an all-encompassing and sustained effort to produce military hardware on an immense scale. This lesson underscored that the nation equipped with the capability to design, produce, and replicate modern weaponry in overwhelming quantities would have a formidable advantage. Such a country could meet its other military needs simultaneously, projecting a force superior not only in the quality and sophistication of its aircraft but also in the sheer volume of material available. Conversely, opponents who managed to develop technically advanced aircraft but failed to manufacture them in sufficient numbers faced a grim, uphill struggle. By late 1943, Germany found itself increasingly vulnerable. The strategic landscape was shifting decisively against it. Britain refused to surrender following France's fall, maintaining its resolve and continuing to build up its defenses. The Soviet Union, having withstood the initial onslaught and orchestrated a strategic retreat beyond the reach of German armies, managed to preserve its industrial capacity and rebuild. Meanwhile, the United States, with an enormous, firmly rooted industrial base that remained largely untouched by the ravages of war within its borders, entered with an industrial might that far surpassed Germany's. In this context, the German leadership recognized that their hopes for victory were gradually diminishing. The window of opportunity was narrowing sharply, and the path to military success was becoming increasingly closed. The capacity to enthuse and replenish their forces, and to sustain the relentless demand for war materials, was now overshadowed by the sheer scale of Allied industrial output. The story of the Beetle and the meticulously studied Thunderbolts at Reekland therefore encapsulates the larger strategic dilemma facing Nazi Germany: how it could comprehend and analyze the military power of its enemies while realizing that knowledge alone was no longer sufficient. German engineers fully understood American industrial capabilities. Each detail of the Thunderbolt's design was carefully examined, thoroughly documented, and officially reported up the chain of command. Nevertheless, this expertise about American aircraft and industrial strength proved insufficient to alter the inevitable outcome. The core lesson of the captured Thunderbolts was clear and uncompromising. In modern warfare, material wealth, when combined with competent engineering, meticulous tactical implementation, and effective logistics, can fundamentally outweigh technological superiority constrained by resource limitations. The most potent asset in American military power was not solely any single technological innovation but rather the entire industrial ecosystem that supported it. This vast enterprise was capable of conceiving, designing, testing, mass-producing, and deploying thousands of complex weapons systems across multiple fronts, all while maintaining high-quality standards and constantly refining designs to incorporate lessons learned from actual combat. The captured Thunderbolt served as an unmistakable testament to this truth. German engineers measured its design details with precision, compiled their findings into detailed reports, and communicated their conclusions up through their military hierarchy with professionalism and accuracy. Yet, unfortunately, this knowledge arrived too late to influence the course of the war in any meaningful way. As the story of William Roach's aircraft, Beetle, and the detailed scrutiny of the Thunderbolt unfolded, the tragic reality became increasingly apparent. The insights gained from these investigations highlighted the fundamental weaknesses invading Germany's strategic position. Weaknesses rooted not solely in sacrifices made on the battlefield but in the inability to match the sheer scale and complexity of Allied industrial effort. The disparity in resources, technology, and factory output was insurmountable by the time these lessons were fully understood, underscoring the ultimate futility of Germany's efforts at that stage of the conflict. By late 1943, an in-depth analysis conducted at Rechlin revealed that the ultimate outcome of the war was being decisively shaped by the burgeoning field of industrial mathematics, an area of study that no amount of German engineering prowess or extraordinary pilot bravery could alter. This emerging reality underscored a fundamental shift in the nature of warfare, where technological and logistical superiority began to outmatch raw skill and daring alone. In this context, the sight of Allied fighters, specifically Thunderbolts, resting on German airfields, their wing insignia hastily covered by retraced markings resembling American stars, symbolized a reality that had already materialized. These aircraft stood as silent witnesses to the fact that victory was increasingly becoming dependent not solely on the brilliance of individual pilots or engineering innovations but fundamentally on the unparalleled industrial capacity of the Allied powers. The war's future had, in essence, been decided long before these planes took off into battle. It was now a contest of manufacturing might, logistical efficiency, and calculated strategic resource management, which had tipped the scales decisively in favor of the Allies.